Okay, so we're now on to video 2 of our standard ASHEE tutorial series. So in the last video, we prepared the file in the system. That is to say, we made this new folder or this new directory called Bloom Test 1. We copied all the standard template for running a standard ASHEE Plume simulation from this directory here into our new folder or new directory, Plume Test 1. Okay, and now we actually want to start modifying the files for our own specific simulation. Okay, so just to check here, pwd, print working directory. We're inside this set scenarios folder here, and I just wanted to point out that if I go in graphically into the set scenarios folder, I can see that there are 4 things inside this set scenarios folder that we've copied. There are 2 folders and there are 2 files. If I wanted to see that using the terminal, what I would type is ls for list, basically list what's in our current directory. And you can see the things in green here are the files. So caseset.sh, so it's a shell file here, corresponds to this file up here. Set.py, a Python file, corresponds to this Python file here. And then the 2 folders, dat and folder 0, are our 2 folders here. So we can actually see what's inside our folder, our current directory, using this command ls. Okay, so now we're moving on to setting up a simulation. So you'd be quite used to opening files in Windows using things like Microsoft Word or LibreOffice Writer, or even something simple like Notepad or WordPad. So in Ubuntu, we have something quite similar called Gedit. Okay, so this is a very simple text editor. And this is nice because it opens in a new app or a new window. So this is a very friendly way to change these files. Alternatively, we can use this thing called vi. And vi basically allows you to modify a file within the terminal itself. Okay, so maybe I'll show you what that looks like. Okay, if I type it correctly, vi. So this command says open the file set.py using vi, and I'll show you if I press enter there, and perhaps make this larger. You can see that everything that's inside this file set.py is displayed here. So we can modify this file from the terminal, and this is something we will need to do when we're running on a cluster. But it is takes a little bit of getting used to, and there are some funny commands with vi. So for the rest of this tutorial, I'm just going to use gedit. We just need to keep in mind that we are going to have to learn this vi at some stage. So I'm just going to quit out of that for the moment. Perhaps make this terminal smaller again. And we're just going to use, for this tutorial, we're just going to use gedit. Okay, so now we're going to open this file set.py using gedit. So I press enter. You can see now that the same file opens up as it did in vi, but now it's slightly more user-friendly, I think. Okay, so let's go through this file line by line. We're not going to change everything in here, but okay. So we're importing some things at the top here: NumPy, some OS, and some sys. So we never change these things at the top. But basically, from line 13 onwards is where we may want to change some things. Okay. So as you may see from the guide that I've written, where is it? I have given you an idea of what each of these variables are. So we'll just go through these one by one. dim is the number of simulations to run one after another. So when we're just running a specific case, we probably just want to leave this as 1. So I'm going to leave that as 1. Res, so this is the number of cells across the vent. So the vent of the volcano eruption, at the moment we're saying we're going to have 4 cells across that vent. So in some situations we might want that to be larger. The problem with that is that it gives us more mesh cells. The more mesh cells we have across the vent, the more we have in the entire domain. So that will slow down the running of the simulation, but in general, that will also give you a more accurate simulation as well. So we always, when we're modeling numerically, we're always trying to balance an accurate simulation versus a fast simulation. So we don't really want to run a simulation that's going to take 6 months to run. But at the same time, we do want some accurate simulations. So often we might run one simulation with a small number of mesh cells across the vent, say 4, and then maybe we might run a more complex or a more fine resolution one, let's say res equals 8, which of course will take a lot longer, but will also give us an idea about how accurate it is to use lesser cells. So for the moment, I'm just going to leave it as 4 so that our simulation runs quickly. Mesh is the type of mesh to use. So there are various types of mesh that we can use in ASHEE. One is this square mesh, which we're going to stick with. One is a cylindrical mesh and one is a Cartesian mesh. I think the simplest thing for our purposes is just to leave this as it is. Okay, the mass flow rate here, this is of course a very volcano specific parameter. So this is in kilograms per meter cubed. So I don't know what we want to do. So maybe let's do a slightly larger simulation. Let's run a simulation with 1 × 10⁸ kilograms mass flow. This should be kilograms per second rather, not kilograms per meters cubed. So I've got some mistake in my thing here. It should be kilograms per second. Okay. All right. TI. So we're ejecting 1 × 10⁸, or let's say 100 million kilograms per second. Seems like a lot, but okay. These volcanic eruptions are large. Here we have TI, so this is the temperature at the vent, basically, at Z equals 0. So the temperature that is of the ash cloud that's coming out of the volcano. I might just leave that at 1200. The next 3 or 4 lines here, this is telling you about the structure of your volcanic eruption, okay, or of your plume. So what this is saying, this 0.05, this is saying 5% by mass of the eruption is water vapor, H2O, so water vapor. 5% is water vapor at the moment. Okay. The next 2 lines are saying that 25% of the solid phase is the large particle size, 75% of the solid phase is the small particle size. Okay, and this is by mass, of course. So in the standard ASHEE case, you can run 2 different particle sizes, and we'll get to setting exactly what they are soon. But basically, we're saying the coarse particle size makes up 25% of the solid phase, and the fine particle size is making up 75% of the particle phase. So we'll leave that for now. And so basically, you can see that this is in total, the solid phase in total, both of these added together are making up 1 minus H2O. So 1 minus the mass fraction of water. So at the vent, when this thing is erupting, 5% by mass is water, and then 95% by mass is the particles, the solid phase, okay? Everywhere else in the domain, air is just going to be equal to 1, okay? So air is just 1 minus everything else by mass, okay? Okay, well, the next few are pretty straightforward. Okay, so we've got specific gas constant for air, Ra, so we probably don't want to touch that. The specific gas constant for water, okay, well, this is fairly constant over temperature range, so we probably don't want to change that either. Specific heat capacity at constant volume for air, again, we don't really want to touch that. Specific heat capacity for water, probably don't want to touch that either. Specific heat capacity for the solid phase, so no matter how many solid phases we have in here, we're going to use a constant heat capacity. So, well, depending on what kind of particles you have, maybe this wants to change. I don't know enough about it. But for now, I'm just going to leave that as it is. Okay, the true density of the solid phases, so the density of the coarse phase or the larger particle class, we're going to say this is 2300 kilograms per cube. The solid density of the smaller particles, the fine phase, is 2700. I don't know, that seems a little bit high, but okay, well, let's leave it as it is for now. But these two are basically the densities of the solid particles, right? The pressure at Z equals 0. So this is basically the atmospheric pressure here. So this value here, 101.325 pascals. This is basically your standard atmospheric pressure, which of course you can change that if you like. If you were having a low come through, you could reduce it, or if you had a high, you can increase it. But this is just your standard atmospheric pressure. Okay, this next pressure here is the pressure at the vent, at the vent of the eruption, when the eruption is happening. So this is going to be something that we need to change. So we'll talk about that in more detail in the next video.